So good morning, everyone. My name is Nguyen. I'm a rising senior in civil engineering at UVM. And this summer, I'm doing a research funded by the Barrett Foundation and under Dr. Scott Hamshaw, Dr. Donna Rizzo, and with the help of my mentor, Ali Javed. And my project is to develop a monitoring tool for analyzing sediment dynamics using water turbidity sensor data. So I want to share a little bit of my motivation for this project. As you can see here is the New York City water supply system. And to everyone's surprise, the New York City water supply system is one of the world's largest unfiltered water supply. And in these recent years, one of the big water quality concern is the excessive amount of turbidities present in the Catskill watershed, which together with the Delaware watershed make up 9% of the water to the New York City water supply system. So to solve this problem, the New York City Department of Environmental Protection decided to implement watershed protection and sediment mitigation projects informed by study on temporal sediment dynamics. They choose this instead of building a filtration plant because it can be very costly. It can cost up to $10 billion for the size of the New York City water supply system. These studies on temporal sediment dynamics specifically look at turbidity and stream flow, and the method that is related to my project is hysteresis patterns classification, and I will talk about that more later. So this is how turbidity sensor look like. Since 2011, the U.S. Geological Surveys has implemented a turbidity sensors network throughout the stream and rivers across the United States. Due to COVID, I cannot go and visit one of those sites, but fortunately enough, I can still have access to all of the data via the USGS National Water Information System, and I can download the data in a text file to my computer. This is how turbidity and stream flow data look like as time series. And every time we see a rising limb followed by a peak and a falling limb, we know that there has been a storm event. For each of the storm events, we want to plot the turbidity against the discharge to get us a hysteresis pattern. And as you can see, the time as third variable is color-coded on the plot as well. Hysteresis is basically a phenomenon in which you see two time-dependent variables experience some time lag. And in this case, the discharge and turbidity reach their peaks at different times, resulting in hysteretic behavior. So we want to look at hysteresis pattern because we can classify them into types, and each type of hysteresis inform us of a different physical process that happened in the watershed. 30 years ago, our technique of data collection is not advanced, therefore we didn't have as many pattern types. Nowadays, with the turbidity sensors in place that can record every 15 minutes, we have so much more data available, and that results in an extended hysteresis pattern library. As promising as it sounds, even though we have lots more data, there are also challenges in processing these data. And with the hysteresis pattern classification method, it's an event-based method. So we cannot use all of the data. We have to go in and select the storm event data. With a large data set like this, going in manually and picking out the events is time-consuming and labor-intensive. So that's why I want to develop a monitoring tool to automate this hydrological event detection and delineation process, as well as recording some useful event metrics for watershed manager, and then visualize the hysteresis patterns. I want to note here that I am not the first to attempt at automating event detection and delineation. However, past research only look at discharge data. in my research, I want to look at both discharge and turbidity data to detect these events. And the site of my study is the Stony Cliff Basin, which is located in the Catskill watershed. And I choose this tributary in particular because they have seen a lot of turbidity issue, and there has been quite a few mitigation projects here as well. So the data is going to be very interesting to look at pre and post mitigation projects. So I developed my algorithm all in MATLAB, and to demonstrate the method I use to automate event detection, I'm going to use the data from the Stony Cliff Creek December 2019. Here you can see the discharge time series, or we can call them the hydrograph. We can say that there are some gap in the data, and we want to fill it in with both moving medians and linear interpolation. Once done, I'm going to smooth the data to get rid of the noise using Savitsky-Golay filter. And after that, I'm going to separate the base flow. So base flow is a very abstract concept in hydrology, but graphically speaking, if you look at the graph, you can see the dotted yellow dashed line here, and that is our base flow. It's basically just a curve that goes through all the local minima of the hydrograph. The method I use to separate the base flow is called the Raman spectra baseline removal using small window moving average. And this is not an application in hydrology, but is actually from the spectroscopy field. So the next step is to subtract the base flow from the smooth discharge. That would give me the normalized discharge as outlined in the purple dashed line. Then once I have my normalized data, I'm going to detect the peak. That gives me the peak time. And from the peak time, I trace back to the start time of the events and also estimate the end time of the event. I apply the same algorithm to turbidity data. Now I have the events from both discharge and turbidity time series. I want to compare them to then decide on the finalized start time and end time of the events. Once that is done, I'm going to plot the turbidity against the discharge for each of the events, which will give me the hysteresis pattern. And yeah, so as far as results goes, I have computed 4 sites in the Stony Cliff Basin from year 2011 till now. I have detected 759 events. Besides recording all of these events, as well as visualizing the hysteresis patterns, I also generate some event metrics that might be useful for watershed managers to look at, including peak, start time, end time, duration, total number of events, and time period. This is an example of how the data would look like in a year. This is the Stony Cliff Creek of 2019 with discharge and turbidity time series and all the manipulated data curves in one plot. Yeah. This is the discharge and turbidity time series in the same graph. And the graph is marked with the start time and end time of the finalized events. And here are all the beautiful hysteresis loops. Yeah, so they take different shape, but the overall trend here is that they are all clockwise loop or open loops. So that's the end of my presentation. This is the sources of reference I use for my research. I would like to thank my advisors, my mentor, and the Barrett Foundation, as well as UVM for making this research possible. Thank you for listening in.